Hey guys, welcome. It's another code update time. Let's see and review what changed. I guess this time it's about halfway there. So after the code changes I implemented today and yesterday, we can get the first halfway decent bridges from our routine. There's some bugs and errors still, but I'm not 100% sure if I can fix them or if I have to talk to Altair to fix them. Because strangely, I get license disconnects all the time. And I assume it's my internet provider, which is cable based. And I had problems with logging into some services like Origin and stuff, and really didn't know why. Because if I changed the network to my neighbor's network, they gave me the code, and logged in with Origin and with different machines, it was working. So I assume it's about latency, cable-based internet connection, stuff like that. All right, shall we jump into the code then? I will just quickly to show you what we have to cover today. Show you the graph here. So more or less, I added all the things from here, but those are rather small ones. This is the main thing. So first I implemented a first logic for the driving lane. So our purpose, or the purpose of this this issue was, let me fix that, let me get that for you. So it was like this, issues, closed, the last one here. So what I wanted to do was, I wanted to specify a driving lane which has no optimization property. That means the solver cannot get rid of them. But I want to have it, because I did that in the last video, so I toggled the optimization from true to false, and that was it. What I wanted to have a logic behind building the driving lane, so that you have, for example, you have your maximum beam length, like in your game, like here. For example, let's go to our basic level. So you have, for example, this is the maximum beam length. So it's 4 grids long. You cannot go longer than 4 grids. Actually, you can, the 3 diagonals, they will work, but 4 diagonals don't. But this works. So it's a little bit more than 4 grids, but less than 1.41 whatever times 4. So square root of 2 times 4. That would be the diagonal. Alright, so you have your maximum beam length, and I wanted to have a logic like do something like this. Find out the driving lane in this way that you have at least elements as possible, as few as you have to use. So don't do something like this because the thing is, as soon you have the driving lane done, right? For example, let's do the stupid approach from last video. You would have to support every bearing here, because something like this. By the way, can you hear the game sound? Yeah, I think you can. Alright, so as few elements as possible, which leaves you something like this, right? But let's consider you have maximum beam length of 3, so something like this. I don't want to have something like this. That would be the easiest approach. So going 3, because that's your maximum beam length, going 3 again, and then you have 2 left. Rather, I wanted to have something like this, go 3 from here, and go 3 from here, and then what's left, you have to find some logic. Actually, you want this, but you could also think of this. But the way it's implemented for right now, it's something like this. You go from each side with maximum beam lengths until you have a distance between the two remaining points, which is less than 2 times the maximum beam length. And then some logic happens, and if it's less than 1 beam length, then something like I just showed you will be done, and if it's more than that, you will have to find a middle node and stuff like that. So this is the first logic, and I implemented that. You can see it here. So, right, we don't want to go into details of this, but there are some flaws in here, which I corrected afterwards. But for the simple test, it worked. So you had different types of driving lanes where you have your node path, which is specified for, in this case, like a set of, or rather a list of nodes, node IDs, and your maximum beam length is 3. And then it should print whatever it has as left, right, and this was the thing here, and it worked for those tests. So for 3 beam length, but also for a beam length which is actually greater than the whole distance, because the distance here is calculated by subtracting one node from the other. So distance from 0 to 1 would be 1, and also from 8 to 9 would be 1. So the total distance is 9, but the beam length is 20, so it should make just 1 beam length, which will never happen in the bridge constructor game, because that would be the trivial solution, no support needed. But this won't be the case, but I wanted to have it here either way. And yeah, so for some tests, also with even and non-even numbers of nodes, I did the testing, and this all worked fine. So this was this. Then I went on to go the thing was, I went there and thought in my head, yeah, you should have to specify your node path. How you will do that? Well, actually, you don't want to have it manually, because if you have some zones where you cannot build, you would want to have a automatic algorithm which finds your way. And the easiest way is to go something like a star algorithm. And this implementation I did here in the grid, which is this block, and also include the source more or less. It's not really the source, but it is the script I took as a basis. And let me show you what this is. This is a description of the A-star algorithm, which is pretty famous. It's used in all kinds of stuff of applications for cable routing and stuff like navigation services, for finding the route between 2 cities, for example. A-star, it's a path finding algorithm. You have a start point, you have an end point, you have something in between where you cannot build, because if it's just from A to B, nothing in between, what you want to have work around with and stuff like that, would be easy, right? You just go a straight line. So a shorter distance between 2 points is a straight line from A to B. But it gets more complicated with something like this. So, and therefore the basic idea is for each point it calculates a cost value, and this is more or less the sum of the distance between the start point and the end point. And there's some logic which you can follow here. There's also some pseudocode, and this is more or less the way I implemented it. Also has the source code, which I also used a little bit of as a basis, but I changed it or adapted it for my needs. But that full transparency, you will have it here. So I did this, and now I can specify a start node and an end node and find a way in the grid. That's good. And then I went on and implemented the whole thing for Hypermesh. And this is also working now, and did some error corrections. So this is the logic where I had to change the way I want to have the rods, because I wanted to have a driving lane eraser, which means I go there and you have your path of nodes already found from A to B, which is your driving lane. And then there is elements, right? The elements would be those elements which you specified at the beginning, like this. I didn't put the driving lane first for some reasons, but I think it can be done also, but I didn't bother. So you have all your elements like this, for example. And now you want to get rid of all of those driving lane elements. And this is what this method is doing. And it's pretty easy. you're giving a path of nodes, and it scans through all the rods, and if a rod contains a node and another node, which both are in the list of your path, it is part of the path, and then it's getting deleted. So this is I think what's happening here, and I think this has got deprecated. Yeah, I think I would use it later on. Not sure about that, but I think I marked that as deprecated because it's no longer needed, because I used the A-star algorithm, which is faster, or no, not faster, but it is more usable in general for general purpose problems. Alright, so rod was changed. Force was changed, a little bit of documentation. Driving lane has now this create rods along the nodes, because, well, it's not that clean right now, but the nodes, which is more or less the specification, are listed like this: 1, 2, 2, 3, which means first rod from 1 to 2, then a rod from 2 to 3, and so on. And this is why the logic here is with step size 2, so it jumps over one element at each loop. So this is a thing to be considered. And also here you can learn a bit about data structure. The DQ is a pretty neat solution, because for a list, you could pop elements just from the end of the list. And you could work with indexes or indices. Both words work. I looked that up. But the DQ allows you to pop left and pop right. So that means you're taking with pop left, you're taking an element away from the queue from the left, so from the beginning, and pop means just your simple taking away an element from the end of the list. So you could make this left, right, things which you use in your driving lane construction pretty neatly. And then lots of changes here. This is the driving lane logic. I changed it here a bit, put some special cases to it, and I think that was it. One thing I missed was we were implementing at the beginning a pretty simple logic of neighbor detection. Not with the distance, but with north, south, east, west. And I changed that to also having included the diagonal elements, which was a pain in the ass. Sorry about the language, but let me see. Was it here? Yeah. So this is the get neighbors IDs, which also include the diagonal elements. And I used it like this, that you have two lists, the neighbors and the active neighbors. So first of all, you're scanning your neighbors, which are present. And that means you have to decide by case, are you in the corner, are you at the border, are you in another corner? And depending on that, I'm a hell lot sure that this can be done shorter, more efficiently, but it's working. And it's more or less readable. So I also commented it if it's bottom right, top right. So for top right, you would have go X to the left, go Y down, and go X left and Y down. And those are the three nodes here. And also be careful that Y is the first index, which is not really that intuitive, but for printing purposes, I took the convention at the start and never changed it. So that's okay, I guess. And then the driving lane logic, the script builder for sure has to change a little bit. There was a serious bug in here in the script builder, which I fixed later here. It was the rod ID got increased before the actual commands implementing the rod. So this is not good, and I put that down. So this is also a thing to be aware of. Yeah, and I think that's about it, right? So added some blackout zones, so this method changed. So if you want to deactivate some elements, that would be fine now. And I think it would be best to just show it here, that you get a feeling of what is possible now. So this is the main method again. You have your thing here. I will just deactivate the blackout zone. I have to find a better name for that. I don't And I don't think that's the right name, but you know what I mean. So it just puts zeros everywhere and deactivates the zones where you want it. And you have your material. And here, actually, the driving lane. Here, that's the interesting part. The driving lane nodes is just the IDs of the driving lane nodes. And here you have your R star algorithm, which is used. And then you have your driving lane eraser, which erases all the rods which are on the driving lane. Then you create an instance driving lane with the max beam length, the driving lane nodes, and the crit as input parameters. And then you create the rods along the nodes path. So this is the actual rods creation. And finally, you create the model entities for all rods. So this is not the driving lane anymore. So this is model entities creation. All right, I think the other things stayed the same, but what I changed here, I changed that it will be using batch as a system preference. So, well, the initial thing here with the displacement was batch already, but also now the optimization will now be batch. So this is also another thing. And I think now we can just run it for once, right? Why not? Let's see what we have here. The max beam length is also now here. It's 4 times spacing. Let's decrease that to 1 times spacing or 1.5 times spacing, because then you get also the diagonals. And what else do we need? Yeah, max beam length. This is great. I think that's okay. No. This one I was looking for. So the neighbor distance threshold is the 1.5. This is for the beams creation. And the max beam length. Yeah, max beam length is 4 times spacing. Because, let's try to remodel this here. So here you have 4 times your grid, right? So that's okay. So it can build something like this, which it will do. And also, I didn't talk about this, but it also takes this as the force nodes and also as the constraint nodes for the displacement. So another bug there I found in the script helper, it didn't really consider the displacements here. So the forces were put on each node here. That worked. But the displacement constraint was only put on the first 2 or something like that. Really strange. It was also a bug in the script builder. So yeah, you find that when you're debugging. But this is resolved. Now let's just run it, right? So I have a calculation folder, ctemp, and I also changed the model names. So ctemp, this is same for the initial run, for getting the max displacement, and also for this one, but the model optimization, no, the name is optimization, so you can differentiate between the two. And also what I wanted to tell you, what was it? There was some important thing here, which I also changed. Yeah, the driving lane rods will be thinner in diameter. Just a thought, because I don't want to have them to be really rigid, as in the game they are not, right? So they break pretty easily. I'm not sure how to go there, but for me at least it seemed plausible to have them with a less diameter. But we can play with this factor around, so this is not really much to change. All right, so let's start it. So we have bridge optimizer, and now Python -m bridge optimizer.bridge optimizer. What? I can type bridge optimizer.bridge optimizer. So there are lots of debug messages here which I should get rid of. So this is the driving lane. So first is segment left 5 to 14, then from right 70 67 to 68 and so on and so on. And those are finally the load nodes, but not necessary anymore. Here you can see the first batch run, and here you can see the second batch run, and also the c.temp will get filled. So I'm lucky right now, no license problems. Great. But what I noticed is that I'm getting errors, and this is concerning some writing permissions or writing sequence. I'm not sure what it caused, but what's the cause of this. But for your model optimization, you will get an out file, which is here. This is what you're getting. You're getting an error, which is something about Bible is closed right now, error during write. I'm not sure, but what I'm noticing is that the out file is not complete. It means that you have now iteration 23 and there's nothing left. So there's no optimization complete, blah, blah, blah. If I'm running the optimization, which I could do, let me just get the compute console. Sorry, it's wrong. As I said, I cannot type anything. Alright, compute console, which was OptiStruct, and just run it again. I'm doing right now. It's the same input, so it would not change anything, and it's rather quick, so I'm doing that. The out file will have not any of this strange behavior. It will get completed without error, and I'm assuming it has something to do with the batch command. I'm not sure 100%, and I have to reach out to Altair about this because I'm not sure where to look. But you see here at the end of my TCL commands, you see that's the line executing OptiStruct. And this is executing the OptiStruct.bat. And then you have an input parameter, which is the FEM file, and some user parameter. I also deleted the user parameter, and I'm not sure what's causing the issue. Because also without any user parameter, I get this error. But it doesn't seem to have any effect on it, on the results. Why do I know that? Because I opened the file and compared it, but also you can see the model optimization 001.out, which is the current one. Sorry, that's the wrong one. So this is the old one, but optimization.out, this is the actual one. This will have finished lines as you would expect, right? So somewhere here, something does go wrong. I don't know why, but yeah, I'm not bothered with that too much at the moment. So let's see what we are getting. I'm opening the results for this particular thing here. It's pretty satisfying to that you're not forced to have opened the GUI Hypermesh and waiting for all the operations, but rather you can really batch execute the thing here. Pretty amazing, I find at least. So 23. At least we are getting now halfway decent bridges, I think, because if you look at it, you could see a scheme of it, right? You have different load paths, which you're seeing here. Sorry. So first of all, what you're seeing is that top and bottom look symmetrical, and that's plausible. And you have certain paths here. And now you're seeing, if you just decrease the number of elements, so this is the only elements with just one as a density, this is what you're left with. And for sure, it's not perfect, but well, actually, from a structural point of view, this is good because you can see all the load paths. It's also all perfect because you cannot, or you don't have to make the, or you must not make the mistake to compare it to the actual objective of the bridge builder, because the bridge builder has this one constraint which you're not having, put as less as possible, as few as possible bearings in it, because each bearing will cost you a lot of money. You saw that with, if you have one, and you see here the counter here, that's just 100 per length. We did that. So the first element costs 400, but then it's just 100 per length. But if you have another one, the first element costs you around 400, and that's because 200 goes for the bearing and then 200 for the first element. I don't know, but you know the amount of elements does play a major role. You have 3000 here, and you have 1200 here. So, in order to win that game, you would have to make a constraint or an objective to use as less bearings or as few elements as possible, and I cannot do that right now with the OptiStruct solver. Maybe in the future, I still haven't talked to my friend yet, but I will do that. And yeah, so for now, this is what it is. But now let's just see a different thing, right? We could, for example, and if that goes wrong, please don't mock me, because it's really live coding here. I didn't test that before. But we could, for example, grid out, just deactivate a zone, which is the bottom one, and then change, for example, the length. Should we do that? Feeling lucky today. So 32 would be a much wider bridge, and then you have your maximum beam length is 4 times spacing. Let's increase that to 8, which would mean 4 elements. Also more forces. And I don't know. No, let's run it like that. And if it's not working right now, that would be rather expected. And you see here, those zeros here are the deactivated nodes, and here are your nodes. So what we're seeing here is that I think the load is applied here. I'm not 100% sure, but I think we have one additional line of rows which we don't really need. But we won't be too bothered with that. Oh, finished run already? So you see the maximum displacement is 5, so much higher than before, because the longer levers. And let's see. Let's go to quickly. The max displacement constraints is 5 times the maximum displacement, so I'm allowing 5 times more the displacement of the full design. And you can change this parameter as well and see where you're getting. But for right now, let's quickly go back to ctemp. So this is now our optimization result. 16 o'clock, yes, that's okay. I'm a little bit nervous about, oh, alright, it's a pretty narrow channel. I think it would have benefited to have a little bit more space to the top, but let's see. There's no prize money to lose here. Well, so first of all, it actually made a difference that you have a line on the bottom. So here's your driving lane. You see that because those elements have 1 density no matter what, because they're not part of the optimization. And let's just, for better clarity, go and ISO show the values here and no averaging. Interesting. So it's not symmetric. Not sure about this, and yeah, you have a lot of new ideas here, because you have more or less the same elements but really tied together. Let's quickly look maybe on the boundaries, and yeah, I should really save the model as well. It's not. We'll use the old Hypermesh right now, if that's possible. I think. and we will just import the .fem file. Alright, Hypermesh, Abstract. Now import on. Oh, alright. Seems to be something broken. Alright. Solver deck and model optimization. Import. It could well be. No, it. I just wanted to say that it could well be that it detected that this is a newer version and will not import it, but it was fine actually. So I want to see the load steps. Well, is this symmetrical or not? So I was specifying 8, right? 8 as a 1, 2, 3, 4, 5, 6, 7, 8. But it's working from both sides. And now you have 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. But it did, for reasons I don't fully understand right now, it did put another rod here. I'm not sure why. So this is another special case, which is in the driving lane logic, which I have to debug. But you see, it works also for larger bridges. So let's see here what he is doing. So left, right, and then you have one final 89 to 104. Well, actually, it has just 4 nodes. 1, 2, 3, 4. Yeah, right. Yeah, it has 4 nodes. That's the problem. Because the load nodes there are skipped for the first and the last, because I'm assuming those are constraints. So there's no reason to put a force here. Alright, now let's think a little bit about what's next after the bug fix here for sure. But if this method is working right now, the next goal would be to have a fully closed loop where I could just batch run multiple optimizations and also getting results that I can read easily. So what I'm thinking about is getting into Hyperview scripting. So to imagine this, you're doing an OptiStruct run, and at the end of the current program, you will then open Hyperview, import your result, then set a threshold for the element density, leave out every element which is below that, export that as a text file, for example. You could do a lot of things with that. But just let's get rid of them, of the text, of the low density elements, and then make a screenshot. Orientate it, fit it, and make a screenshot, save it, next run. And I want also to have the database, a database to have the values, the input values included, so that I know what I'm changing. And there is some things I'm not quite sure about right now. How I want to do this, maybe with a markdown template, which puts every simulation in a separate folder and then combines all of the pictures into one summary report. That would be quite fascinating. But I'm quite sure I'm not getting that done in 1 day or 2. But yeah, so it will be maybe a little bit of time until the next release. Well, next release, it's not a release, the next video update. But I think it would be good to have a process like this for future research or for future experiments here. Alright, bug fix this thing, and I think we're making progress on this. So yeah, now begins the fun part. Now I can get to different bridges and also make some, just forget about the blackout sounds, the deactivated sounds. Yeah, I should include that as well. Make it a little bit better and see if it works. Because yeah, there's a lot of special cases. If you have a blackout zone within your node path, then but that's taken care of the A-star algorithm. Sorry for me being here a little bit confused, but There's just so many ideas running in my head right now. Alright, batch run, bug fix, batch run, and then I will do the blackout sounds. As always, thanks for watching. Thanks for your interest. If you have any comments, questions, you're free to leave them down below. You're free to leave a like, a subscribe if you liked what you're seeing. And yeah, I'm seeing you in the next video. Goodbye.